Hey, Professor.
Hey, how's it going?
I'm doing well. I was wondering if I could ask you a quick question on the homework before class
Sure.
starts.
Yeah, sure. What's up?
Could I share my screen?
Yeah, let me go ahead and enable it. And I need to stop it here.
Cool, cool.
Okay, go for it.
Thank you, thank you. It's on number 3. I just have more of like a question about like what to plug in, I guess, for
Okay.
some like values.
Mm-hmm.
Let me see. So I set up the thermal circuit like how you gave us like the hints in class last time,
Mm-hmm.
and then I started solving for the heat transfer.
Uh-huh.
And I got to this part, right, where you have like the total resistances
Yep.
set up. So what do you plug in for A? Since like in this case our like pipe, right, it's like a square.
Yep. Mm-hmm.
And I wanted to ask like would you plug in for A and then would you plug in for like the shape factor? Because in the notes, like the ones you have like posted online, table 4.1, it has like certain scenarios.
Mm-hmm.
So are we supposed to get the shape factor from the one in the textbook?
Yeah, so the one I have in the notes is incomplete. And
Yeah, yeah.
so the one, if you look at table 4.1 in the book, you should see a scenario that looks basically exactly like that. So I think for this one, you'll have to look in the book for that one. Um, And then for A, remember A is the surface area here. So if you kind of imagine like you have a square pipe, the way that you compute the surface area in this case would be to compute basically the perimeter of the square and then multiply by the length. And so I think I gave you, yeah, so the length into the page of this pipe is 10 meters. And then you
Yeah.
just multiply that by the perimeter, either by
Okay.
the inner perimeter or the outer one. And that would be the area that you plug in for that.
So like I said, it doesn't matter. You could choose either inner or outer.
So it depends for which one that you're talking about. So for our convection one in your case,
Oh,
that's
okay. For the
that's the
inner
inner.
perimeter.
Exactly. And then our convection two would be the outer perimeter.
Oh, okay, cool.
Yeah.
That helps.
Hmm.
Thank you, thank you.
Hmm.
So, Professor, how's your day been?
Wait, was Hutton, will you say something? I couldn't hear you.
Yeah. Oh, I was just asking you how your day was.
Oh, it's good. Yeah, I made curry last night, so I was eating the leftovers for that for lunch today. So it was good.
Oh, nice.
How are you?
Pretty good. Upgraded my computer recently, so
Nice, nice. You upgraded it for gaming, or would you upgrade it for?
I mean, a bit of gaming and just like run other stuff because like I built my computer like 4 or 5 years ago, so
Okay,
it was just starting to chug along and have crashes. So I just upgraded the CPU and the motherboard.
I see, I see. Yeah, 4 or 5 years. That's about the time to upgrade upgrade your computer. Cool, cool.
Yeah, my bank account took a pretty big hit for that.
Yeah, I've heard the price of computer parts has been going up lately because everyone's been building their own rigs and upgrading their computers in the pandemic.
Yeah, I mean, for those two parts, and I actually got a pretty good deal on it. It's about $400.
Uh-huh. Yeah, even with the deal, that still sets you back quite a bit.
Oh yeah, definitely. Well, if you're able to like resell your old parts, then usually helps out quite a bit.
Hmm. Okay, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today?
Not too bad. How about yourself?
Good, good. Yeah, it's definitely, you know, get semesters in full swing. So I know we have the midterm next week, and I'm sure you guys are really busy with midterms as well. Okay, and so today the plan is to finish up our lecture notes on transient conduction. So this is the last topic that's going to be on the first midterm. And so after today, today is kind of the lecture, after the end of the lecture today, that's the cutoff for the first midterm. So everything up until the end of lecture today, all the way back to week 1, that's going to be the first midterm. Okay. And so our first midterm, remember, is next Wednesday. And so that's going to take place in class. And so on Monday, I posted the study guide for that. So were you guys able to look at the study guide, or at least able to find it and download it? Yeah. Okay.
Yeah,
Good.
I got it.
Good. Yeah. So definitely use that study guide to help you out. To help guide your studying. I would say a good way to study for my exam is to start with the study guide and just go learning objective by learning objective, and just make sure that you can do all those things, and then go through all the homeworks as well. Okay. All right. So besides that, we have a homework 3 is due on Monday, and so I know that's right. Right pretty close to the exam, and so usually I wait until after I grade your homeworks before posting the solutions. But since this homework is going to be due right before the exam, I'll post the solutions basically right after the deadline is passed. And so by midnight, or I'd say 12:01 a.m. on Tuesday, you'll have the solutions for homework 3 to help you out, with your studying as well. Okay. And the other thing is that after the class today, probably sometime, this afternoon, I'll put a poll on Canvas, and I'll email you guys and link it to you, so you can vote on the topics that you feel most uncomfortable with, so far that we've covered in the class. And then what I'll do is I'll take the top 2 or 3 responses from that poll, and then make a review video, probably sometime Friday afternoon, and post that on YouTube to help you guys study as well. Okay, so that you guys get some kind of extra explanation and extra example problems for the ones that you feel most uncomfortable with. Okay, and so keep an eye out for that poll. Definitely vote on it, and I need the responses for that poll fairly soon. So by the end of tomorrow, I need the responses from that poll so that I can make the review video. Okay, it's not required, so the poll is anonymous, so I don't know who answers what. But the more people to vote, the more likely it is for it to be effective for the class. Okay. Okay. And so, are there any questions that I can answer before we get started today? Okay. All right. So let's go ahead and pick up where we left off. Right. And so just like I just mentioned, we're working on transient conduction. All right. And so the idea with transient conduction is that these are heat transfer situations that change with time. Okay, because before this week we were only looking at heat transfer scenarios that were steady state or that didn't change with time, right? And so in order to analyze this, we are using a method called a lump capacitance method. Where because normally if you're solving a time-dependent problem for heat transfer, you have a partial differential equation to solve, and no one likes doing that. Okay, but with the lump capacitance method, where we make one very key assumption, we're able to reduce that PDE into an ordinary differential equation that we can solve for. Okay, and so that ordinary differential equation is given by the following. Okay, so we have minus HA, or rho VC, times theta is equal to d theta dt. Okay. Remember, the key parameter here is theta, where theta is the excess temperature. Because most of the situations that we'll be looking at with transient heat conduction are situations that look like this, where we have maybe a large tub of liquid, okay, and then we have some object, okay, could be like a potato or a piece of metal or something like that, okay. Right, and then there's a difference in temperature between the objects. So the object is at some temperature T of T, And then our environment, or our fluid that's surrounding it, has a temperature T infinity. Okay. And our excess temperature here is just the difference in between the two. Okay. Right. And so, this isn't new. So we've seen this concept of theta and excess temperature back when we were discussing fins. It's just that now we're applying it to, transient heat conduction as well, just to kind of simplify the math for us. Okay. And remember, the key assumption that we make in the lump capacitance method is that this object here, this object is at the same temperature all throughout, okay? And so it's the same temperature on the edge of the object as it is at the center, right? And that's key because we're basically ignoring any kind of spatial variation in the temperature at all, right? And then if we solve this equation, we just simply do a separation of variables. We get a very simple solution, okay? So we get theta of T is equal to E to the minus HA over rho VC T, okay? And so we have this decaying exponential, we have this decaying exponential where, the temperature difference is maximum at T is equal to 0. And then as the object, gets, either absorbs heat or it releases heat into the fluid, the temperature difference between the object and the fluid starts to decrease because the object starts to become closer in temperature to the fluid. Okay. All right. Any questions on this so far? This is just kind of recap from last time. Okay. And so I think specifically where we left off is we were looking at a specific example of dropping an ice cube into a tub of water. Okay. And so in this case, the ice cube starts at a lower temperature than the surrounding water. Okay. And we're going to assume that, we're dropping it into like a swimming pool or something. So, normally when you drop an ice cube into a drink, your drink is a relatively small amount of fluid. So as the ice cube heats up, then your drink cools down. And that's the reason why you put ice in your drink, right, to keep it cool. But if you throw your ice cube into a very large body of water, like a swimming pool, then the ice cube is going to heat up and eventually melt. But because the swimming pool is so vast, then the temperature of the swimming pool itself doesn't really change all that much, okay? Right. And so when we solved this, the lump capacitance method, we got the following graph for theta of T, right? And so it started at our initial temperature difference, so we'll call that theta I, right? And then eventually it kind of zeroes out like that, okay? Okay. And so let me, just for completeness, let me write out the formula solution for this again. Okay? So theta of T is equal to theta I exponential to to the minus HA over rho VC T. Okay. Okay. And so now for the rest of this example, I'm going to show you, several different things that you can do with this equation, because there's a lot of interesting questions that you can answer. And right now, I'm keeping everything just in terms of symbols, but I'll show you kind of how to set up the equation to solve for some interesting things. Okay, so the first thing I want to solve for, or first thing I want to show you that you can do with this equation is say that you want to find out how long it's going to take the ice cube to reach a certain temperature. Okay. Right, and so the key word in here is how long, right? And so this tells us we're going to solve for a time. Okay. Right. And so basically we're going to use our equation here, but we're going to plug in for theta of T on the left-hand side of this equation and then solve for T itself, okay? And so let's say that we want to solve for the amount of time it takes for the ice cube to heat up to a new temperature, and we'll call that new temperature theta N. Okay. And so new temp for ice cube. Okay. All right. And so we're going to set this equal to our equation here. So we're going to set it equal to theta I e to the minus HA over rho VC. Okay. And then we're going to solve now for Tn right here. Okay. Okay. And so from here, it's just working out the algebra. So let's go ahead and divide both sides by theta I. And so we have theta n divided by theta I is equal to e to the minus HA over rho VCT. Okay. Or Tn, I should say.
Is that a greater than or equal to?
It's an equal sign. Oops.
Okay.
Yep. iPads being weird. Okay. And so now that we're at this point, remember we're still solving for Tn, and so we need to remove the exponential. So let's take the natural log of both sides. Okay. Right. And so we end up with the natural log of theta n divided by theta I is equal to minus HA over rho VC Tn. Okay. And then we can just multiply both sides by the inverse of this exponent, and then we can solve for Tn. Okay. Okay. Any questions on this? Okay. All right. And so we multiply both sides by that inverse, and we get the following. So we have Tn is equal to minus rho Vc over HA times ln of theta n over theta I. Okay. Right. And so basically given, once you solve for theta of t, you can solve for the amount of time it takes for, for the temperature to reach a certain value. Okay. Okay. And so that's one thing that you can do with this equation. Okay. All right, so the next thing is more of a conceptual question. And so, part 3 of this question asks, what happens if you have a larger ice cube? And so in other words, what happens if the volume of the ice cube increases? Okay. Okay. And to be more specific here, I want to ask, how does this affect the time evolution of temperature for the ice cube?
Quick question, Professor. That A in the equation, is that surface or cross-sectional area?
It's surface area. So it's the total surface area of the object. Mm-hmm.
Oh, that's right. Okay.
Okay. And so in other words, let's say that V is increasing. Okay. And in particular, let's assume that, the ice cube is a certain shape where when we increase the volume, when you increase the volume, naturally the surface area of the ice cube is going to increase as well. But let's say that the volume is increasing at a faster rate than the surface area. Okay. And so in other words, if we have our solution that looks like this, right? So we have theta of t is equal to theta I e to the minus HA over rho VC T, okay? And so that's our temperature solution here, right? If V is increasing at a faster rate than A, then what's happening is that this exponent right here, or this coefficient from the T, is getting smaller. Okay, because remember, volume is on the bottom. And so if we increase the volume, then that's going to make the overall thing smaller. okay? And so the way that it affects our temperature distribution looks like the following. So normally, you know, we have something that looks like this, okay? So we have our decaying exponential. But then if we increase the volume, what's going to happen is that the rate at which this graph decays is going to go down, okay? And so instead of a rapid decline like that, we're going to have a slightly slower decline, you know, maybe something like that. Okay. Right. And we kind of talked about this last time too, right? So last time we talked a lot about, you know, what are some physical features of your object that can affect, you know, how quickly or how slowly its temperature responds to its environment. Okay. And so if you have a case where the volume is increasing, then your object's getting bigger, then it has more heat, or you know, it takes longer for, you know, for the object to mask the temperature of its environment. Okay, just because it has more mass, you can kind of think of it like that. Okay, and so for this part, you know, basically if you increase the volume of your ice cube, you know, and the surface area is you know, not growing as big, then you're going to get a result where the temperature decays a little bit slower. Okay. All right. Any questions on this? Okay. All right. So the last thing I want to talk about, which is kind of an interesting one, is you know, let's theorize what happens if we took this ice cube and we threw it into a pit of lava instead of a swimming pool. Okay. And let's assume that the lava has the same, you know, the same value of H. Okay. All right. So the convection, the convection inside the lava, we'll say is about the same effectiveness as the swimming pool. Okay. The only difference is that, you know, lava is obviously at a much higher temperature than swimming pool water, right? And so what's going to be different here is that the initial temperature difference between the ice cube and the fluid is going to be much higher. Okay. Let's say theta I much higher. Okay. All right, so let me write out our solution here again. Okay. Okay. And so we have theta t is equal to theta I times e to the minus HA over rho VC t. Okay. And so if the only thing that's changing here is theta I, right, then obviously we're going to have a graph with a much higher initial temperature difference, right? Okay. And so, you know, we're probably starting way over here instead of, you know, our swimming pool, where maybe we're starting over here. Okay. Right. What's interesting about this is that, you know, even though the initial temperature difference is different, if everything else in this problem stays the same, the rate at which the temperature, you know, changes in the ice cube actually stays the same, right? And so you're going to end up with a graph that actually looks something like this, right? And so for the lava, you might have something that looks like that, okay? But for the swimming pool, you know, it's going to look like something like that, right? Right. So this is kind of a paradoxical result. So, you know, if the only thing that you're changing in your situation is the temperature, in the initial temperature difference, the rate at which your object is changing temperature isn't affected. Okay. Which is kind of, you know, crazy to kind of think about, right? So if you throw your ice cube into a pit of lava, or if you threw your ice cube into a swimming pool, you know, the rate at which, you know, the temperature basically reaches its final temperature is about the same, right? And so in reality, of course, this is not true because, the one big assumption that we make here is that H stays the same, okay? Right? And so in reality, probably if you throw your ice cube into a pit of lava, the H or the convection coefficient for that one's going to be much, much higher. And so, your ice cube is going to melt and it's going to, accelerate, its temperature difference. But, if you assume that that's the same, then you get basically the exact same rate because this theta I, or the initial temperature difference, doesn't enter into this exponential term at all right here. Okay. All right. Any questions on this? Okay. All right. So let's talk about the validity of this lump capacitance method. Okay. Because so far we've analyzed time dependent situations with this seemingly simple ordinary differential equation, but kind of the fair question to ask is how valid is this and when can we actually apply this? Because it would be great, if we can use this method for all time-dependent heat transfer problems because it's relatively simple, but that's not really the case, right? And so to kind of motivate this, let me kind of draw the situation again. Okay, so here's our object. I'm going to draw it a little bit bigger, okay? And let me draw a boundary around our object here. All right. And so, just because our object here is, it's sitting in a fluid, of course, we're going to have some convection heat transfer. And we'll assume that the convection heat transfer is going into the object for now, okay? Just for the sake of, of having to draw an arrow, but this logic will work whether the convection is going in or the convection is going out, okay? And then besides the convection heat transfer, which happens at the surface, there's also conduction heat transfer that's going throughout the object itself, okay? Okay. And so the way that you can think about it is once the heat enters the object through convection heat transfer, then that heat can then penetrate through to the middle of the object through conduction heat transfer, okay? Right. And so remember our assumption here. So our assumption that was key to the lump capacitance method is that the temperature of our object is uniform throughout. If you think about this assumption according to this figure that I've drawn up here, one way that you can kind of think about it is that Q conduction here has to be really, really large relative to Q convection, okay? Okay. Because, if this is true, and so if heat can conduct through your object much more easily than it can convect from the outsides, then any heat that enters from the object from the outside gets immediately transferred through the rest of the object through conduction, right? And so if basically the speed of conduction in your object is much higher, then this assumption that we're making is valid, okay? Right? Okay. And so it would be nice if we can come up with a number or a way to kind of assess whether this is true right here, right? So if there's something that we can just simply plug into, to kind of assess how the ratio of these two guys, then that would be nice. Okay, and so let me give you this number right here. And so let's say we want to compute the ratio of Q convection over Q conduction. Right? And let's plug in some physical parameters that have to do with these guys, okay? And so convection usually depends on the convection coefficient h, right? And so let's put h in the numerator there. And then in the denominator, let's put a physical parameter that governs conduction. And so let's use K, where K is the thermal conductivity of our object, okay? And then just to make sure that the units for the top and the bottom match up, let's multiply it by some length L, okay? Right? And then in the end, we have this dimensionless number right here, right? So do you remember from fluids about dimensionless numbers? So you should remember about, things like the Reynolds number, where, these numbers don't have dimensions, but they represent important ratios that can tell you a lot about the physics of the situation, okay? And so this here is I think, probably our first dimensionless number for heat transfer. And this dimensionless number is known as the Biot number. Okay. Right. And so if you want to assess whether the lump capacitance method is valid, the way that you would do that is you compute the Biot number, okay? And generally, if you compute your Biot number and it's less than 0.1, then in these situations, then the lump capacitance method is valid. Okay. Right. And so this threshold of 0.1, I'll be the first to admit it's a little bit arbitrary. And so, the way that they came up with this is through, a lot of experiments. And so from experiments, basically what they've been able to show is that if you compute the Biot number and it's less than 0.1, then you can assume that the object is basically uniform temperature, okay? Right. And so if you go back to, how we kind of motivated this ratio here, if the Biot number is less than 0.1, that means that Q conduction is at least 10 times faster than Q convection, okay? And so whatever rate that the heat is entering the object with from convection, that heat can pass through the object at least 10 times faster, okay? And if that's the case, then, you can assume that the lump capacitance method is valid. All right. Any questions on this?
So then the like the NASA material used for rockets is very low or high?
Yeah, that's a good question. I would assume you're talking about like thermal insulation kind of materials.
Yeah, like where
so-
you re-enter.
Right. So in those cases, I would say the Biot number is really high for those ones because those have a very low thermal conductivity. And so if you have a low number of value of K, then this is going to increase your Biot number. Yeah.
Okay. Thank you.
Mhm. Yeah. So typically objects with a low Biot number will be objects with a high thermal conductivity. So we're talking like metals, we're talking solids, things of that nature. So things with, very high thermal conductivities. That's not to say that you can't get Biot number less than 1 for other materials. It's just that you need to increase H quite a bit.
Professor, under the Biot number, it says lump capacitance, and then what's the other word?
It says valid. Yeah.
Okay.
Yeah. So basically you can use it. There you go. So basically, whenever you have a time-dependent situation, or where the heat is changing or the temperature is changing with time, the first thing that you should do, you should always compute the Biot number to see if you can actually use the lump capacitance method. Okay, and so if you get Biot number less than 0.1, then that's great because then you can use your lump capacitance method, which is mathematically a lot easier to work with than the full heat equation. Okay. And so this, luckily the Biot number here is fairly simple. So it has, quantities that we can, easily pick off from the problem. So as H and K, the only thing that might be a little bit hard to choose is L right here. Okay. And so L here is some length. And so I kept it kind of vague on purpose. And so, the question is, how do we choose the length of a three-dimensional object? Right? right? And so whenever you have a length that shows up in a non-dimensional number like this, we usually call that a characteristic length. Okay, so we call that LC. Okay? And so for some objects, it's fairly simple to compute the length. So let's say that you have a rod, right? So for the length, you can either pick the radius of the rod or the length. Okay, but if you have something that's fairly complicated, like say like a roast chicken or something, then it becomes a little bit tricky. So how do we choose the length of this roast chicken, right? So I mentioned that because I've always wondered, is a roast chicken, can you use the lump capacitance method on a chicken that you're baking? And the answer is no. I've already done the math for it. But if you have if you do have a complicated object for that, this is typically what you do. And so if you look at your object and you can't find a characteristic length, what you can do is you can take the volume of the object and then you divide it by the surface area. Okay. Okay, so up here is volume. Down here is surface area. Okay. And so if you take this ratio of volume to surface area, then this gives you, a length that you can plug into the BO number. Okay. And so if you're ever in doubt of like a certain object, what do you plug in for a characteristic length? Just take the ratio of its volume and surface area, and then that gives you just fine. Okay.
When you're talking about the complicated bodies like the chicken, do we like make a broad assumption like for the chicken, assume like it's a cylinder shape or something?
Yeah, so it's so if you're just thinking about just a chicken in general, you can do that, so you can approximate its shape. But if it's something that you can physically measure, yourself, or if you have like a CAD file of it or something, then you can kind of just measure the volume and the surface area that way as well. Yeah.
Okay, thank you.
Mm-hmm. Yeah, most often, when you're using these kinds of methods that we talk about in this class, a lot of times you're going to be using them, in the design or the analysis stage. So a lot of times you either have a CAD file of your object, or you have some good measurements that you can compute these things. Yeah. Mm-hmm. Okay, so one more concept that I want to talk about before we jump into another example, and that is the time constant. Because another thing that's usually interesting to compute for transient heat conduction is a lot of times we want to know how quickly can our object react to changes in its environmental temperature. Okay. And then to do this, we're going to look at just basically the rate, right? And so we kind of looked at this a little bit at the very beginning of lecture today, where we computed, how long it would take the ice cube to go from one temperature to another, right? And if you remember, the thing that primarily determined this was, the coefficient in the exponent, okay? And so if we define our time constant, so we'll call this tau t to be rho Vc over HA. And so, where I got this number was from our theta solution, right? So if you remember, our solution for theta was theta I e to the minus HA over rho VCT, okay? All I did was I took this, this number right here and I just inverted it, which is like what I got there, okay? And what's significant about this is that this, the units for this guy of rho VC over HA, this has units of time. And then by computing this, it'll give us an idea for how long it would take for your object to kind of react to changes in its environment. Okay, because look at its role in theta of t right here, right? And so remember, let me draw a graph of theta t again. Okay. Okay. Right. And so our theta of t, remember, is a decaying exponential, right? And so this, this factor that I've circled in green right here, that basically determines the rate at which it decays, okay? And so certain objects, depending on its physical parameters, so depending on its value of rho, its density, its volume, its heat capacity, and its surface area, right? So different objects are going to react differently, or they're going to react at different rates compared to other ones, okay? And so this time constant right here gives you a sense of for how long it would take your object to react. Okay? And if you're designing, you know, certain types of devices, and so in this next example, we'll look at a thermocouple, you know, computing this time constant is actually really important because there are some times where, you know, there are some cases where you want your object to react very quickly to changes in its environmental temperature. And there are some cases where you want it, you know, to not react as quickly. So it all depends on the situation. And so if you, you know, just so, and so by computing this time constant right here, it'll at least give you a good sense for, you know, how long that takes. All right, any questions on this before we jump into an example?
That's a subscript C for the V, right? Or is that separate C?
It's a separate C. So that
Okay.
C is thermal or heat capacity. Yeah. Okay. All right, so let's do an example. So do you guys know what a thermocouple is? Yeah, so a thermocouple is basically, you can almost think of it just like a thermometer. So it's a thermometer that kind of is at the end of a wire. And so, you know, visually what they look like is, you know, you have a thin wire and then there's a little bulb at the end. And then you're going to put that bulb onto, you know, whatever you want to measure the temperature for, and then it reads its temperature. So, you know, a lot of thermal experiments use these thermocouples. Okay. And so in this example, let's assume that we have a thermocouple that's in the shape of a sphere. Okay. Okay. And so here's our thermocouple. And let's say it's attached to a wire right here. Okay. And what this thermocouple is responsible for is that it's responsible for measuring the temperature of a very hot gas. Okay. And so let's say out here we have a hot gas. Okay. And then let's say that it has these properties right here. So let's say that the gas temperature is 200 degrees C. And then its H is 400 watts per meter squared K. Okay. And then let me give you some properties for the thermocouple itself. Okay. And so let's say that the thermocouple is made of a material which has a thermal conductivity of 20 watts per meter K. Right? Let's say that its heat capacity is 400 joules per kilogram K. And then let's say that its density is 8,500 kilograms per meters cubed. Okay. All right. And so in this problem, you know, we're designing this thermocouple. And so the first thing that we want to find out is, you know, what diameter can we choose for this thermocouple to achieve a time constant of 1 second? Okay. Okay. Because the thing with thermocouples is that, you know, you always want them to basically measure your temperature accurately, right? And so a thermometer doesn't really do you any good if it's not measuring the temperature, you know, accurately. And, you know, let's say that we're in a situation where the hot gas, the temperature of the hot gas is changing, you know, fairly rapidly. Okay. And so generally what we expect from this situation is that the temperature of the hot gas is changing about every second. Okay. And so what we want our thermocouple to do is we want to design it such that, you know, we can pick up these fluctuations in temperature, right? And so in other words, we want the temperature of the thermocouple to react within 1 second to changes in the environment. Okay. Okay. And so, say if you're designing an experiment like this, or you're designing some kind of device, this is going to affect, which thermocouple that you buy from the manufacturer, because you want to choose one with a diameter, that works for this. Okay. All right. Any questions on this? Okay. So let's go ahead and work through the problem. Right. And so, since we're computing how long it's going to take the thermocouple to react, naturally, we're going to compute its time constant. Okay. Right. So our time constant is given by the following. So we have rho VC over HA. Okay. And so we're given everything in the problem. And so we know the density of the thermocouple, we know its heat capacity, and we know the H for the hot gas that's around it. The only thing that we have to compute here is the volume and the surface area, okay? And of course, this is going to depend on the geometry, but since we have a thermocouple that's a sphere, what we can do is we can compute its volume. In terms of its diameter is pi d cubed over 6, okay? And then the surface area for a sphere in terms of its diameter is pi d squared, okay? All right. And so let's go ahead and plug this in, okay? And so let's go ahead and plug in for tau T2, right? So remember, tau in this case is going to be 1 because we want the thermocouple to react, within 1 second. Right, so I'm going to pull out rho C and H because those we know in the problem, and then we're simply just going to take the ratio of its volume and surface area. Okay. Okay. And so for the volume, we have pi d cubed over 6, and on the bottom we have pi d squared. Okay. And so all of these are going to cancel out right here. Okay. And so in other words, we have 1 is equal to rho C d over 6h, okay? And then if we solve for d, we see that d is equal to 6h over rho c, okay? And then we plug in all the numbers, and then what we get is a diameter of 7.06 times 10 to the minus 4 meters. And so in other words, our thermocouple needs to have a pretty small diameter in order for it to react to temperature changes in the temperature of its environment, okay, within 1 second. Any questions on any of this? Okay. All right, so now that we know the diameter, now we're going to check to see if the lump capacitance method is valid. Okay. Because if the lump capacitance method is valid, then we can model this with the lump capacitance method, which is really nice. Okay. And so remember to check to see if the lump capacitance method is valid, we're going to compute the BO number. Okay. So remember, BO is equal to H times L over K, right? Where L in this case, L is simply just going to be the ratio of volume to surface area. Okay. which we computed up there. And so our Biot number is going to be h over k times d over 6. Okay. Right. And if we plug in all the numbers, what we get is a Biot number of 2.35 times 10 to the minus 3. And there's no units on the Biot number because it's, it's a dimensionless number. Okay. Right, so now that we've computed the Biot number, now we can check to see if it's less than 0.1. And in this case, it is less than 0.1. So, we're good to go. Right. And so since, our Biot number is that small, basically what we can say is that, the heat is going to conduct through our sphere at a much higher rate than it is going to convect through the outside. Right. Any questions on this example here?
Could you explain again how you got L to be the volume over the surface area?
Yeah. So in this case, it's a sphere, and so you can argue to say that for a sphere you have a length that's very clear here, which is the diameter. But for some cases, let's assume that our thermocouple was some kind of weird amorphous shape, right? And so in those cases where you can't easily compute a length to plug in for the Biot number, you can take the volume of the object divided by its surface area. Because a lot of times, you want to do this lump capacitance method on a 3-dimensional object. And so for 3-dimensional objects, sometimes it's hard to choose, what length to plug in for a Biot number. Because all the Biot number says is that you have h times length divided by k. And so, in the worst case scenario, and, this is, and I'll say this is fairly safe to do in a lot of situations. For L, you can just take the ratio of the volume and surface area. And then that's what you can plug in.
Oh, thank you.
Mm-hmm.
Professor?
Yep. What's up?
Let's say it was like an I beam then.
Mm-hmm.
Would we then just do volume over area again?
Yep.
Okay.
So this volume over area thing works for most objects. Yeah. Mm-hmm. Okay. So that's everything about the Biot number and the time constant. Now let's talk about general lump capacitance analysis. Right. So up to this point, we've been doing the lump capacitance method, but we've kind of been doing it in a very simple case, right? And so, and what I mean by that is that the only factor or the only, way of external heat transfer from the object is through convection. Okay? And so, in other words, the only thing that we've considered is just convection heat transfer from the object. But in reality, kind of in a more general situation, you have lots of other ways an object can gain or lose heat. Okay. Okay. And so just to name a few, and so in one case, we can have a prescribed heat flux. And so let's say that, we're purposely heating an object from the outside, right? And so just kind of a simple example, let's say that you put your pan on a stove, right? And so the stove is going to, heat your object with a, prescribed heat flux. Okay. Right. And so another way that an object can gain heat is thermal generation. Okay. And so if the object can produce its own heat, and so, I have an example here where, if you've ever used a heating pad before, or like a hot pack, you'll know that, the way it works is that you kind of crack it, and then there's some chemical reactions that take place within the object that causes it to heat up. Okay. And so, that's another way an object's temperature can change. And so if it either generates its own heat, or if it consumes heat, that's possible too. And so a third way, which I'll admit for now we're going to neglect, is radiation. Right? And so radiation, kind of the black sheep of heat transfer that we'll kind of ignore up until the end of the class, right? But radiation is a valid form of heat transfer as well, right? And so if you apply radiation to an object, say you microwave something or you stand outside in the sun, then your temperature is going to change as well. Okay. Right, so right now we're neglecting all of these. So right now we're only considering convection heat transfer. But what we can do is we can modify our lump capacitance method to account for all of these guys. Okay. Okay. And so this is going to make our differential equation a little bit more complicated, but I'm going to do a big example here to kind of show you how that works. Okay. And so the only caveat is that I'm going to say that we're not going to consider radiation. So because radiation is still a bit too complicated from where we are in this class. And a lot of the times radiation is fairly negligible compared to the other stuff. Okay. And so we're kicking him off the island for now. Okay, so let me draw, because I don't think the equation will fit here. So let me draw kind of a figure here that will kind of illustrate this. Okay? And so let's say that we have our object here. And so just like before, let me draw a control volume around the object. Okay. And so before, up to this point, we've only considered convection, right? So let's say that we have an object or a fluid that's out here. Right? Right? And so from convection, we will have, heat transfer into the object or out, and so we've seen that before. Right? But in addition to this, you could also have thermal generation. Okay. And so let's say that our object itself is generating heat, and so we'll call that Q dot. Okay. Another thing we can have is we can have the object, or we can have a prescribed heat flux on the object. Okay. And so, we'll call that heat flux QS double prime. Okay. All right. And so basically what we're going to do is we're going to take the lump capacitance method that we have already and then modify it, to also include this purple term and the green term. Okay. All right. Any questions on this? Okay, so let's go ahead and start modifying our equation. Okay, and so in the base lump capacitance method, we have the following. Right? Okay, and so in base lump capacitance, we have rho Vc times dt dt, right? And so this is equal to Q convection, right? So that's what we had before. But now we're also going to add the other stuff. Okay, so we're going to add QS double prime plus Q generation. Okay. Okay. And so let's fill in the expressions for all these guys, right? And so first thing is, well, let me draw a minus sign here because we need that. Okay. First thing is, let me fill in the formula for Q convection. And so Q convection here, we're going to use Newton's law of cooling, which is what we've used before. Okay. Okay. And so Newton's law of cooling, we have HAS times T minus T infinity. Okay. Next, we have our prescribed heat flux. Okay. Right. And in order to transform a heat flux into a heat transfer rate, remember we have to multiply it by an area. Okay. Right. And so I'm going to multiply by A sub Q right here. Okay. And so this Q, this A sub Q, okay, you can think of this as the area on which the heat flux is acting on. Okay. And so this is usually different than the total surface area, because usually when you apply a heat flux, you're only doing it on a small portion of your object. Okay. Okay. And then finally, I'll use purple for that. That's fine. And then finally, we have Q dot here. Okay, so remember Q dots are thermal generation. And in order to transform the units from thermal generation to heat transfer rate, we have to multiply by volume. Okay, and so we're going to have V times Q dot. Okay. And so if you plug all that in and you kind of move some terms around, then you get the this final expression here for the general non-capacitance. Okay. And so we're going to have dt, okay, plus HAS divided by rho VC T. Okay. So notice here that we're not doing our substitution for the excess temperature, although you definitely could. You know, that's definitely an option for you here. But I'm going to show you kind of just the general you know, general lump capacitance where you don't make that substitution. Okay. Then we have the you know, the term for the environmental temperature. Okay. Then we have our heat flux terms. We have QS double prime, A sub Q divided by rho VC, okay, plus our thermal generation term, which is Q dot divided by rho C. Okay. And so that's our formula for general lumped capacitance. Okay. Okay. And so I will say that, you know, most of the time you're not going to work with all of these terms at the same time. And so a lot of times you're going to apply some assumptions to cancel out some of these terms. Okay. Okay. And the assumptions that you make are usually pretty clear from the problem. Okay, so a lot of times the problem will explicitly say that there's either no thermal generation or there's no heat flux or something like that, or sometimes there might be no convection as well. Okay. All right. Any questions on this before we jump into an example? Okay. All right, so let's do an example here, which is inspired by my kitchen, right? And so let's talk about the heating of a cast iron skillet. Okay. And so here is my terrible drawing of a cast iron skillet. Okay. Yes, it's awful, but it's okay. Okay. All right, and so let's say that you know, on the bottom of our cast iron skillet here, we're going to have our flame, and so you know it's sitting on the stove. Okay, and we'll say that the flame is imparting some heat flux onto your skillet. Okay. And then over the top of your skillet, you know, you have your fan going, right? Because You don't like it when the fire alarm goes off in your apartment, and so you turn on the fan to wipe away the smoke. But because of that, you have airflow that's going over the top of your skillet that's cooling it. Okay. And so that airflow has a ambient temperature T infinity, and so we can say that that's basically room temperature, and then H, which is its convection coefficient. Okay. All right, and so in addition to this, you know all the physical properties of your cast iron skillets, and so we know its density, okay? We know its volume, we know its specific heat, and so all of those are known, okay? We also know its total surface area, okay? Okay, so we'll call that AT, okay? And we also know the area on the bottom of the skillet. So this is the area that's exposed to the flame. Okay, and we'll call that AB. Okay. And another thing we know is we know the initial temperature. The initial temperature will say that the cast iron skillet starts at room temperature. Okay.
Sorry, what was AT or AB, or what was the difference?
Yeah, AT is the total surface area of the skillet. So the total surface area around it, and then AB is just the surface area that's on the bottom of the skillet, and so that's just the area that's exposed to the flames, basically. Yeah.
Is AB the same as AQ?
Yes, AB will be the same as AQ. So that's where we're going to plug it into the equation. Mm-hmm. Okay. And so our initial condition here is that T of 0 is equal to T infinity. Okay. Okay. And so the first thing that we're going to do in this problem is we're going to use our lump capacitance method to solve for the time evolution of temperature. Okay. All right. And so in this problem, since we have a heat flux that's going on, we have to use our general lump capacitance. Okay. Okay. And so let me write out the full expression for general lump capacitance, and then we'll cancel out terms as they're not relevant. Okay. Okay. And so here is our general lump capacitance formula, right? So this is what we wrote on the previous page. And so let's look at each of the terms here and see, which ones that we're going to keep. Okay. All right. So first we have our time derivative term. Okay. And so we're going to keep this guy. We always keep this guy. Otherwise we have no, nothing to solve for. Okay. Okay. Next we have our convection terms. Okay. And so obviously here we have convection, and so we're going to keep those guys. Okay. Next we have our heat flux term. And we can see here that we have heat flux, and so that's all good. Okay. And then finally we have our thermal generation term. Okay. And so nothing in the problem says that this cast iron skillet was generating temperature, right? So it's not a self-heating pan. I don't think anyone's invented that yet. Which might be a good idea. And so in this problem, we're going to eliminate that guy from the equation, okay? And so we don't have that much of a simplification, but at least we have one thing that we don't need to worry about, okay? Okay. And so at this point, we can save ourselves a little bit of math here, and then, write this equation with the excess temperature. And so if we make the substitution, theta is equal to T minus T infinity, what that'll do is that'll combine both of these green terms right here, okay? And that'll make our equation just a little bit easier to solve, okay? Right, any questions on this before we start working through the math? Okay. All right, so if we make that substitution and then we start filling in the values of the parameters, and so for this example, I'm doing everything in terms of symbols, but in the homework problem, I do give you values for all of the parameters. Okay, and so we end up with this differential equation here. So d theta dt plus hat all over rho vc theta is equal to qs double prime AB divided by rho VC. Okay. And so this right here is the equation that we're going to solve. Okay. Right. And so at this point, you have to kind of think back to your, previous classes on differential equations. So either 308 or math, I think it's 250A. Okay. And what you should notice from this equation is that it's a first order differential equation because we just have a first order derivative, okay. But it's non-homogeneous. Okay. And it's non-homogeneous because we have this term on the right here for the heat flux, okay. And so you can solve this equation, whichever way you feel most comfortable. I know that there's, several ways that you can solve this. And so you can either solve it with a characteristic equation, find the, find your homogeneous solution, then add the non-homogeneous solution. And so that's fine. And so that works. But usually for these types of problems, I like to solve it with an integrating factor. Okay. And so our integrating factor, we're going to take basically this coefficient here in front of our theta and then put that in our exponential. Okay. And so we can basically say that our integrating factor, which we'll call mu of t, is equal to e raised to the integral of hat divided by rho vc dt. Okay. And so we perform that integral and everything is a constant up there. And so we get e to the hat divided by rho vc times t. Okay. Okay. And at this point, what you can do is you can take your integrating factor and multiply it by your equation. Okay. And if you do that, and if you kind of remember from your ODE class, the reason we do that is because it turns the left side of our equation into a perfect differential. Okay. And so what we have here is that we have d dt of theta times mu of t. Okay. And so that's what the left-hand side of the equation simplifies to. And on the right-hand side of the equation, we have what was there before. So we have qs double prime AB divided by rho VC mu of t. Okay. Right. Right. And so that's kind of the magic of the integrating factor, so that we get that left-hand side. Okay.
What was the mu of t?
So the mu of t is this guy which I'm circling in purple, and so that's our integrating factor. And so this is just a method to solve the differential equation. Yeah. Okay. Okay. And so now that we have the equation in this form, what we can do is you can just simply integrate. Okay. Because the left-hand side is a perfect differential, right? So we have d dt of that stuff. And so this integral and this d dt are going to cancel each other out. Okay. And so on the left-hand side, what we have is theta of t times mu of t is equal to qs integral of qs double prime ab rho vc. And I'm going to go ahead and plug in for mu of t here. And so mu of t is e to the hat over rho vc t. Okay. And so when we integrate this guy, the only thing that's a function of t right here is our, our exponential. And so, by performing that integral, then this guy out in front, the time constant, will just kind of pop out in front just like that. Okay. All right. Any questions on this so far? Does this bring back memories from previous classes, hopefully?
Sadly.
It's nasty.
Yeah, I know I've had a few of you guys in my 308 classes, so I know for sure that we went over this, but hopefully that this is familiar for a lot of you guys too. Okay. All right, and so when we perform that integral, what we have is theta of t e. Okay, and so I'm going to go ahead and plug in for mu of t on the left-hand side, and so we have e times h a. All over rho VCT, okay? And this is equal to QS double prime AB all over rho VC, okay? Times the factor that pops out from the integral, which is rho VC over HAT, okay? Times e to the HA over HAT all over rho VCT, okay? And then we have to add our arbitrary constant C here, right? Because we, are performing an integral here. And so we have to have our arbitrary constant, okay? We can perform some simplifications here. And so we have rho VC on the bottom and rho VC up top here, okay? These two areas don't cancel out because, one is AB and the other one's AT, okay? And the other thing we can do is we can take what's on this side of the equation and divide it through, okay? And so that's going to cancel out this guy and then put a term on that C term, right? All right, and so in the end, we get theta of t is equal to QS double prime AB all over HAT, okay? Plus C E to the minus HAT over rho VC T, okay? All right. And so we're almost done. And so the last thing that we have to solve for here is our constant C, okay? And then to solve for that, we're going to apply our initial condition. And our initial condition was that, our pan was the same as room temperature, okay? So we're gonna have theta of 0 is equal to 0 here, okay? And so if we solve, so if we plug that in, what we get is C is equal to minus QS double prime AB over ATH, okay? And so in the end, what we get is theta of t is equal to QS double prime times AB over HAT times 1 minus E to the minus HAT divided by rho ACT. Okay. Right. And there's our final answer. Okay. Right, and so the last thing I'll do for you on the next page is I'll plot the solution, and then we'll call it a day. Okay. Okay. any questions on this solution here? Okay. Oh.
What's the e to the power of? It's to the power of negative HAT over PAC.
Yeah, it's rho AC. So on the bottom is a density times the oh, sorry, it should be rho VC. Sorry, thank you. Yeah. Thanks for catching that. Okay. All right, so real quick, let me go ahead and plot this for you guys. Right, and so the plot is going to look something like this. Okay, where eventually, you know, the pan is going to reach its steady state temperature. Okay, where this steady state temperature right here is QS AB over HAT. Okay. Right. And so in other words, you know, your pan will it will take some time to heat up because it's cast iron, right? And then the eventual temperature that it reaches, it depends on QS. And so it depends on how strong your stove is, basically. Okay. And it also depends on the ratio of the bottom area compared to the total surface area of the pan. Okay. And so the bigger your bottom is, you know, the more, the higher temperature is going to reach. Okay. And then on the bottom there, you have H, which is the convection coefficient of the air, and the total surface area. Okay. All right. Any final questions on this? Okay. All right. So we're out of time for today. And so, and you know, with that, you know, you should be able to do the rest of homework 3. And so we covered everything about problem 4 and problem 5 today. And so you should be good to go to finish that homework by Monday. Okay. But of course, you know, if you have any questions about anything, you know, definitely let me know. I think problem 5 might be a little bit confusing, you know, so don't be afraid to ask questions on that. And then keep an eye out for that poll, which I'm probably going to put out later this afternoon. Okay. And so make sure you vote on that poll so that, you know, the review session will cover the topics that you want. Right. And so with that, you know, best of luck studying, guys. You know, definitely, you know, start studying early so that you'll, you know, the midterm's just a week from now. And, you know, I'll be available as much as I can over the next week. Okay. So have a great weekend, everyone. You know, have a good rest of your day, and I'll see you guys next week.
Thanks, guys. Have a good one.
Thanks, you too.
Hey, Professor.
Thanks, guys.